When we've looked at integration so far, we've looked at how we can find the area between a function and the x-axis. What we're going to do now is have a look at how we can find the area between two curves. And you can see here we've got two functions mapped on this graph here. One way we could do this rather crudely, just like when we looked at integration in the first instance, is trying to approximate it using geometry. So we could say that here, for instance, if we're trying to find the area of this rectangle, well, we could find the area of all these rectangles, and that would give us a rough idea of the area between the two curves. And to find this area here, we could see that the base of the rectangle is going to be the difference between negative 1.5 and negative a half. So the width is going to be 1, and the height, to find the height, we can find the y value here. So if this is f of x, we can find f of negative 1, and we can subtract g of negative 1, and that will give us the height of the rectangle. And provided this one is always greater than this one, then that will give us a positive value. So we can find the height and the width of this rectangle, and similarly we can repeat it for each of these rectangles. So you can try and complete this table and find an estimate for the area. This should give you, if you complete the entries here, an area of 35. However, that's not particularly accurate. You can see this inaccuracies in these sections here. We've got extra sections here, and we're missing sections here as well. So in principle then, one of the things we could do is we could increase the number of rectangles to make it a better fit. And remember, that's essentially what we're doing with integration. We are increasing the number of rectangles such that the number of rectangles becomes infinite and the width becomes infinitesimally small. And at that point, we can use integration to find the area. So we would integrate the difference between the larger function and the smaller function. So in this instance, we would integrate, this is the larger function, so we'd integrate between negative 1.5 and 3.5 for f of x minus g of x. And if you do that on your calculator, you should get an answer of 35.4, which is fairly similar to this, but just a little bit more accurate. We can generalize this and say that for any functions y1 and y2 which are continuous between a and b, and for which, and this is the crucial point, y1 is greater than y2 in all, for x in all this range, then the area between y1 and y2 is given by the integral. So this is the key formula which we're going to be using. The integral between two values b and a, with the intersections here, the integral of y1 minus y2 with respect to x. So let's have a look at a couple of questions. So we'll go through the first one together, and then you can have a go at the second one by yourself. So we're told graph the region bounded by the curves y equals x squared minus 2 and y equals negative x. Write down an expression that gives the area of the region, and then find the area without using a GDC. So we can see here these are fairly simple functions, so we should be able to sketch those without too much trouble. We need to find the points of intersection. So the first thing you do is start with a sketch of y equals x squared translated down 2 units and y equals negative x. So we can see that here, in this instance, the region is where y equals minus x is greater than y equals x squared minus 2. This is defined, this region is defined by these two boundaries at which point our two functions are the same. So all I've done here is set y equals x squared minus 2 equal to negative x, and you could solve this on a calculator. Maybe you could solve this graphically using a GDC, but here it's non-GDC, so we're solving it algebraically. That gives us a quadratic, which we can solve then to find the points of intersection at negative 2 and 1. So we don't actually need the y-intercepts, it's just the x-coordinates at these points, which will define the boundaries of our integration. So we can then integrate between negative 2 and 1 for this function, the larger of the two functions, minus this function, we can express that as we can expand and simplify to give us this expression here, which we can then integrate by using the addition or subtraction rule, so we can integrate each of these components individually. Once we've done that, all we're going to do is substitute in for 1, which gives us this value, and then subtract, having substituted in for -2, which gives us this value, and if we expand all that out, that gives us 9/2. So I'll invite you to have a go at this question. This is f of x equals 2e to the negative x over 2, that should be there. And g of x equals x squared minus 4x. So you can use your GDC. Just have a go at this and then follow the answer 3. So again, first instance, you're going to sketch them. So just even though we've got more complicated functions, we can use our GDC, so plug them straight into there and see what's happening. First thing we can do then is find the intersections. So here you could solve it graphically, and from the intersections we can see that's going to be -0.58 and 4.06. So those are going to be our boundaries. We can then integrate between these two boundaries for the larger function, 2e to the negative x over 2, minus our smaller function, and using our calculator that gives us an answer of 14.7. So we've looked at situations so far where the y1, our first function, is greater than our second function throughout. What happens, however, when we have something like this? So write down an expression that gives the area of the region between fx equals 10x plus x squared minus 3x cubed and g of x, which equals x squared minus 2x, where we're asked to find the area. So I'll just give you a moment or so to play around with this and then follow the solution 3. So for this, I would always encourage you to draw the graph. Now, this is problematic because we can see here that in this section, our quadratic is greater than our cubic. However, in this section, our cubic is greater than our quadratic. So if we try to integrate this whole thing, we would end up with a positive and a negative value, which would not represent the area under the curve. So in fact, what we've got to do is, if you recognize or find the intersection points, there's an intersection here, here, and there'll be one over here off the edge of the page. So we can find those, again, either graphically, it's a GDC question, or algebraically. We end up with the solutions -2, 0, and 2. Therefore, we are going to integrate, in this instance, between -2 and 0, where the quadratic is larger, and then we're subtracting the cubic. We then need to add the integral between, this is going to be 2 and 0, for, in this instance, where the cubic is larger than the quadratic. Now, because this is a GDC question, you can just throw this in and generate the answer of 24.